Hi, my name is George Gadanidis. Thank you for inviting me to your conference. It's a pleasure to be here. Today I'm going to be talking about computational modeling in mathematics education. The agenda is to consider what do we call this thing that we do with coding and mathematics. A lot of people in where I work call it computational thinking, and we're finding that that label doesn't work very well for us, and we're switching over to computational modeling, so I will talk about that. But before I talk about those things, I think it's important to give you some examples of the work that we do, so you can situate why we're considering this. So CT, computational thinking, or computational modeling in math education. Which holds the most promise in math education? And perhaps you may suggest a different label. We'll come back to these questions. Labels matter. However, without examples, they're just words. And this is why I'm sharing with you these examples. So example number one, the way we work in classrooms is by asking teachers, what do you need help with? So grade 3 teachers I was working with in a school in Ontario, Canada, said, do you have any ideas for teaching area representations of fractions? So we designed an activity where students would walk out the door or to the door. And to get to the door, of course, you have to first get halfway there. And when you're halfway there, you have to walk half of the remaining distance and half the remaining distance and so on. So this is one of Zeno's paradoxes. Now, if you don't think about it, you can walk to the door and pass it. But if you think of all the fractions in between, it seems like impossible. How can you do an infinite number of steps and still get to the door? So students took each of the fractions that they walked and represented them as areas. So they shaded squares like this. So there's the first one, half, the second one, half of a half, and so on. Then students were asked to take scissors and cut out the shaded parts, and then put them together to make another shape. How big would that shape be? I mean, it goes on forever. So you're constantly adding forever more and more pieces, shaded parts. Would it fit in their classroom? Would it fit in the universe? How big is it? It's easy for students to notice that all the shaded parts fit within one of the original squares, and that it's possible to hold infinity in their hand. This is important for us, that feeling of surprise. We purposely design activities so students experience the pleasure of mathematical surprise and mathematical insight. We also interview mathematicians. So in this case, it's Graham Denham from Western University. And as you can see from that image, he's considering, what if we look at just the square pieces and separate them from the ones that are not squares, and have each of those go towards the corner of the square. So you can see that together they make one square, but what fraction represents each of those? You can see that the ones that are not squares are twice as big as the squares, so you've got a ratio of 2 to 1. So that would help students to get to that answer. Interviewing mathematicians is purposeful because we want to see whether the activities we're doing would interest mathematicians. Is this mathematics interesting to a mathematician? Is this mathematics worth talking about, if you want to talk with others? We believe in the work that we've done that occasional, well-designed, aesthetic mathematics experiences that offer surprise and insight raise expectation and anticipation of what mathematics can offer. Many students in classrooms don't have an idea of what mathematics is. So we're trying to broaden the perspective, and we think that helps them pay attention to mathematics because it becomes more interesting, more complex, more human. If you want to see some of these in action, we created some videos. The URLs are, I'll share my PowerPoint with the conference, and they're welcome to share this with you as well. So or you can pause the video. I think this is a video, and you can type in the URL. So we also do coding activities to extend these. And in this case, we're using Python. We use Python as young as grade 3. We like Python for listing numbers because if you try to do it in Scratch, the problem is you can't print on the screen with Scratch. You have to create a list, you have to populate a list, you have to empty a list. There's a lot of coding involved just to print on the screen. With Python, here we have 6 lines of code. And with those lines of code, we can do 2 different things. We can list all the fractions. You can see them getting smaller and smaller and smaller, plus their sums. And we can see that it's getting larger and larger, but it doesn't seem to be getting bigger than 1 at all. It's getting closer and closer to 1. You can also, with more complex code, you can also print the graphs on the screen. So you would have the green, which is the sum of the fractions, and the blue, which is the fractions themselves. So you can see that the fractions getting closer and closer to 0. Will they ever reach 0? Will the sums ever reach 1? So if you think about walking to the door, you always reach the door. I mean, you always walk those fractions and you still get to the door and beyond. So you must reach the whole distance to the door. So these ones must be equal to 0 in one case and 1 in the other case. Here's a Scratch program that we use. This doesn't list numbers, but it simulates a bug walking towards a strawberry. And the code just takes 4 steps, half, quarter, 1/8, 1/16, and then stops. So now students can change that and take more steps to see if it makes a difference. They can also consider putting in different fractions. Maybe 1/2 isn't big enough. What if you use 3/4? Will that get you to the strawberry? Maybe 9/10 or 99/100. Does that make a difference? The second example I want to share with you comes from, again, from a grade 3 classroom where a teacher said, do you have any ideas for teaching symmetry? So we designed an activity where students experience symmetry as a transformation that leaves an object looking unchanged. So this is how symmetry is defined in mathematics. However, in school, symmetry is often an attribute. For example, the letter A has a line of symmetry, the letter Z does not. So it tells us something about the letters or the shapes, but it's not an action. We don't do anything with them. So that's a little bit like, you know, looking out the window here and saying there are 25 trees and 2 boats. Now, what I did is I labeled 25 trees and boats. But imagine if I didn't have any operations. If I couldn't operate with the numbers, I couldn't add them or multiply them. How much mathematics could I do just by labeling things? Either it has a line of symmetry or it does not. It's 5 trees instead of 4 trees. So what we do in the classroom, the teacher in front of the class has a square in her hands, and she says, close your eyes, and I'm going to transform the square. Then they open their eyes and they say, well, it doesn't look like you did anything to it. It looks the same. What could I have done to it so it looks the same? Well, they said, maybe you did nothing to it. And the teacher would say, that's possible. It's possible to do nothing. That's an acceptable transformation. Just like you can take the number 2 and you can add nothing to it, or 0, and that's acceptable. You can do that, and you still get 2 out of it. But what else could I do? And then students start discovering the different transformations, like you can rotate it, and you can flip it, and so on. We also then, we wanted to use Scratch initially, but the problem with Scratch is it does rotate nicely, but it doesn't flip, it doesn't reflect. So you can't do reflections. I mean, you can write code to do that, but then it becomes very complex. So we created our own coding environment using Blockly. And here's the first version of that program, which is getting students to rotate and reflect squares and see what happens. So you can see that that we also labeled the square with dots in the vertices, 1, 2, 3, 4, so you can see its orientation. In this case, what you're seeing is that this square is rotated 90 degrees. So starting from the upper left-hand corner, used to be 1, 2, 3, 4, and now it turned 90, it became 4, 1, 2, 3. So those permutations on the left that you see, those numbers 1, 2, 3, 4, 4, 1, 2, 3, can be seen as labels, attributes, but you can also see them as transformations. So for example, if you look at the square that's there on the screen, and I said to you, do 4, 1, 2, 3, you would then have to rotate it 90 degrees because that's an abstract instruction. It's not saying put it so that it looks 4, 1, 2, 3, but rather, no matter what it looks like now, take the fourth vertex and make it first. Take the first vertex and make it second, and so on. So you can see how we're getting, with very young students, a sense of abstraction just by looking at the permutations. They love the word permutation, by the way. And then we consider, well, we've only discovered 8 permutations, 4 for rotations and 4 for reflections. How many are there altogether with the numbers 1, 2, 3, 4? So students create organized lists. And they circle the permutations that are rotation symmetries, and they underline the permutations that are reflection symmetries. Now, can you tell them apart? If I showed you a rotation symmetry permutation, would you know that that's what it is and it's not a reflection? Can you tell this by looking at the order of the numbers? So that's a question to consider. So you can see new mathematics emerges when something becomes a transformation, as something that changes other things. It's an action. So when students, I was working in a grade 2-3 classroom, and one of the grade 2 students called me over and said, there's something wrong. And I said, what's wrong? He said, I did 2 reflections and I got a rotation. I said, that's interesting. Why don't you try 2 different reflections? So he tried some more, and he was always getting rotations. And I said to him, boy, it looks like you may have discovered something new. And you looked up at me and said, math is so cool. Now, it's interesting that at such a young age, you can make these discoveries. I have to do underneath of this is, the essence of closed or open sets, groups or not groups. In this case, if you reflections, you might say, like to meet other transformations, whereas the rotations hang with each other. They always stick with themselves. No matter how many rotations you do to a rotation, it's always a rotation in the end. But if you flip or reflect something twice, so imagine you have this piece of paper that's a square. You flip it once, and you flip it again, it goes back to this side. And on this side live all the rotations. You can rotate all you want, you're always on this side. If you flip, you go to the other side. Flip twice, it's a rotation. Flip 3 times. So if you do an odd number of reflections, you're going to get a reflection, an even number. So you get a rotation. And students discover this as well. Now, these tools are tools to think with, as Papert said. So it's not like we create them and then we have a purpose and that's the end of it. They affect us as well. They change the mathematics that we can do. They changed how we do the mathematics, but also give us new ideas about what we can do with them. So for example, we thought, what if we just put the symmetries in this sandbox and let them go? So in this case, you can see at the bottom that we have the 4 rotation symmetries, 0, 90, 180, and 270, and they're different colors. And these are the 4 reflection symmetries. So we put these 4 rotation symmetries in here, and with the code, we ran the code, and now they're randomly moving and bumping to the sides and then bumping against each other. So you can see here that the blue and the green bumped into each other. Blue is 90, green is 180. So then now they're going to transform each other. The 90 is going to rotate the 180 90 degrees more, so it becomes 270 or yellow. And the 180 will reflect, and the 180 will reflect the 90 180 degrees more, and that will become yellow too. So if we let this go, those two that bumped each other will become 270 or yellow. So the question now is, if we let this go, what would it look like in the end? Can we tell? So I was working in a grade 6 classroom, and we did this for the first time in that class. And we did all the other activities with symmetry, and then we get to this one. And I said to them, what do you think? And I said, if you have an idea, come up and whisper it in my ear. And 3 students came up. And all three students had a different answer, and all three answers were correct. One student said they're all red. One student said they're all going to be 0. And one student said they're all going to be 360. Those are all the same thing. And it makes sense because 0 is the only stable state. It doesn't change anything. Whereas if you had all blue, when the blues bumped each other, they would change to different symmetries. It would not be stable. So the only stable state is all red. So interesting that those students were able to see that before they even tried it. We also thought, you know, we have these symmetries bumping into each other, but what happened to them, you know, is something that happened in the past and we forget about it. Can we track it somehow? Can we create data that we can look at after all the bumping that happens? So what we did is, if two symmetries bump each other, then we record the result. So the 90 and the 180 gives us a 270, which is, and they're both going to be 270, which is yellow. So then you'll see a splatter on the screen that's all yellow. However, if two symmetries bump each other and the result is two different symmetries, one for each other, for each square, then it becomes two different colors in the splatter, as you can see. So the question now is, what would we expect to have all the colors distributed evenly, like the same number occurring the same amount of times, or not? So to do this activity, to design it, took a long time because, you know, initially when teacher said symmetry, I thought, oh, what can I do? It reminded me of group theory, abstract algebra. I looked at my abstract algebra textbook from university. It wasn't really helpful, very helpful for something that I can do with grade 3 students. So it took a long time to read about the history of abstract algebra, look at books that people have written about symmetry, and so on. The first one, that was about infinity, that was easy because I had already done that when I taught calculus. So now that's the kind of work that we do in classrooms. How does this help us? How does this definition of computational thinking? Computational thinking, according to Google's course on computational thinking for educators, and similar descriptors are used by Wing. So computational thinking is about decomposition, pattern recognition, abstraction, algorithm design. So if I'm thinking of those things, how does it help me design what I just designed? I can't imagine it being that helpful to me as an educator, as a researcher. So it's poorly defined, first of all, because all these things that you see here are also part of other subjects. Mathematics, abstraction is at the heart of mathematics. Algorithm design, of course, you design a way to solve problems. All these things belong to other fields as well. So what we've done when we use the label CT, we didn't focus on these descriptors. What we focused on were the affordances of the tools that we used. What did they afford us? What could we do differently or better? And we identified 5 things. You can put more on this list or less, but this list we didn't create this list from scratch. Other people have talked about this. Papert talked a lot about agency. He talked about low floor and high ceiling. So he talked, you know, the fact that you're dynamically modeling. Others have as well. So it's not like we invented this, but rather we recognize that all these things that those people talk about are what we actually are seeing in the classroom. So access, low floor, high ceiling. You can teachers notice that, look at this student and look at that student. And we ask, what is it that we're looking at? And what they're saying is they're doing things that they don't usually do. They're performing at a very different level. They're interested. They're talking about mathematics. Agency. In one of those classrooms that I worked in a grade 3 classroom, this was the first coding activity. And we did what you see at the bottom there, which is do squares in a spiral pattern. So once we modeled that physically and did the coding as well, and then students were to try and create their own, this young student came up to me and she said, I'm going to make my own. I'm not going to copy what's on the screen. I'm going to do something new, and I'm going to call you and say, watch this. So that's agency. Abstraction. Well, you know, if you look at that code there on the bottom right, it says define shape. In Scratch, you can define your own code blocks. So we defined a code block called shape. And that shape could be any shape. We can change the repeat to 3, change the angle to 120, and we have a triangle instead of a square. And that code that's general or abstract is also tangible, has a tangible feel, because you put it in some other code and you can do things to it. So abstraction gets to have a tangible feel, which is interesting and important. And automation, obviously, you know, if you're going to do this by hand, it will take you a long time. You make a change, you have to do it again. Here, you make a little change, click on the code, it runs dynamically. You can see what's changing. And audience, students take things home. It's easier to share digital artifacts. And also within the classroom, students are talking to one another more. Becomes more collaborative. They're sharing. They become an audience for one another as well. Issue number 2, are coding skills the goal? I mean, are we teaching, or are these general abstract, you know, descriptors like abstraction? You know, our students become better at abstraction. Generally, not in mathematics, but generally. DeSessa said that, contrasted the view that most people use coding for in education as programming for programmers, rather than programming for users to tinker and create. Barba, working as a computational scientist, suggests that this takes us on a detour from the original powerful idea envisioned by Seymour Papert more than 30 years ago. She said these tools are a source of power to do something and figure things out in a dance between the computer and our thoughts. But the inversion, starting with the computing as a formal thing to understand and then come to the application later, takes away its power. Also, there's a lack of attention to what happened in the past. It's as if computational thinking in education just happened. It's been going on for a long time, and it's been going on in mathematics education for a long time. Seymour Papert's work with Logo, he saw Logo as a coding environment and as a mathematics learning environment. He wrote that Logo is to learning mathematics what living in France is to learning French. And there you see the code in Logo. PD, pen down, FD, forward, 100, RT, right turn, 90, do it 4 times. You can put it in a block and make it repeat 4 times. I like that version of Logo. I wish Scratch had that option as well. And also, there's been research done in the past. Noss and Hoyles wrote about Logo, summarized their research, and said that Logo did not deliver all of what it promised because due to a failure to address non-technical aspects, such as the social, cultural, pedagogical context into which Logo is inserted. Those statements, the description I shared with you from Google and also from Wing, it's as if you do coding, you're going to become good at those things. Yeah. But in your classroom, teachers are teaching mathematics, they're teaching other subjects. How do they become any good at those things? Yes. So there's this belief that this generic skills are going to develop, and there's a history that shows that that's problematic, that idea. And this failure has been repeated today, as others, as I just said, and others have written about. Computational modeling, on the other hand, is a way to shift the computing and education focus to what computing does. Turning our attention to turning our attention to what computing does very well, which is modeling. So if you look at the world around us, excuse me, the use of computational tools to model phenomena, processes, and relationships is becoming a prerequisite to scientific progress and economic success, as evidenced by the emergence of numerous computational modeling fields, such as computational biology, computational mathematics, computational finance, computational medicine, computational chemistry, and so on. So, what's next in the work that we're doing? Well, one project is, a playful project called Wonder, where we are putting these things together, videos, coding in, and we call it a Wonder, and because that is something that humans are good at, wondering, being attracted to wonder, and we put 7 wonders in here, and we're hoping to have a second issue. So this is one project that we have. Another one is the Ontario curriculum right now, Ontario and Canada, was just changed to have coding in mathematics in grades 1 to 8. So every grade level is going to have coding in it in algebra, along with modeling. So it's a very powerful change. It has a lot of potential. It's not easy to implement these things well, but hopefully, and so we're creating as well, trying to help, like others are trying to help, by creating these resources for teachers. And we're offering them at a very low cost. $4 gets you all this for the whole year, and any updates. Also, storytelling. I really enjoy and working with others writing stories about mathematics. So there's one there on Symmetry, which allows you to, as a teacher, to go through the story and pause and then do the activities, and a couple of other ones. And the project that I'm working on now is called Ideas That Travel. So the question of that is, how do you share a good idea so others can share it too? How do you structure it? How do you engage people with it so it becomes something that is worth talking about? They want to say it too. They want to talk to somebody about it. Yeah. Thank you so much for listening. There's the website where you can get information on all of these things. There's my email if you have any questions, and there's my Twitter account. Thank you so much, and I look forward to your questions and discussion and comments.